This is Aaron from the Caradron team again. This video is actually about the control algorithm. This is the Caradron control panel from my earlier video. The screen right here actually has our total complete control algorithm. This was displayed on our last A3. Actually, the control algorithm displayed on the last A3 actually had a manuscript error. The A3 had the feedback loop from the log, from the yaw coming from the absolute orientation. It does not come from absolute orientation. It comes from the raw gyroscope reading, so we can see rate of change. So that was a little small error. That's just mainly a documentation error. Let me actually zoom in on this. We're going to go down to this bottom part right here. This is the feedback loop. It starts with the IMU, which is a combination gyroscope, accelerometer, magnetometer. They are being filtered by third order low pass Butterworth filters. I'm going to show you the code for that here in a second. So this is the gyroscope, this is accelerometer, this is magnetometer. The gyroscope is basically combined with previous data. It pretty much generates a rate of change quaternium, basically for dimensional data, while this part down here is giving frame of reference to the Earth. This is a PID controller. Basically, the way this feedback loop works is the gyroscope is the set point, the accelerometer and magnetometer is the metric point. And the assumption here is that the gyroscope is a cheap piece of crap and that there's associated error with it. And what the this PID controller is doing is correcting for magnetic distortion and also correcting a very cheap sensor as well. This is what's called Group 1 out of the MADRC algorithm according to his dissertation. We did not implement the Group 2 PID controller, which would have been a second PID controller out over here that would account for gyroscopic drift. We chose not to implement that one because we would not be running more than 15 minutes. If we needed to go longer than a 15-minute flight plan, we would have needed to implement the Group 2 part of the feedback loop. So it's then integrated to reveal absolute orientation. That quaternium is then normalized. It is just normalizing the vector. And then we convert it to Euler angles, which is roll, pitch, and yaw. We need to go up into the actual control loop. We would pull our input in from the RC receiver, roll input, pitch input, yaw input, throttle input. They're all filtered. The reason we're filtering this is the accuracy of the receiver is not great. The unfiltered receiver can fluctuate between numbers like 53 and 55% very quickly. So what the third order low pass Butterworth filters are doing here is kind of smoothing that out to where we don't quite see that fluctuation. It does add a little bit of filter delay, which, to be perfectly honest with you, the filter delay thrown in there feels right on the controller. So we're not too concerned. Then that data, roll and pitch, their PID control is control absolute orientation, basically position control. They're pulling from the feedback loop. The yaw is just pulling the raw gyroscope data. This is basically yaw rate is what it's controlling. So the yaw is actually not pulling from the main feedback loop. The throttle is completely open loop. It is just it's filtered and then it's sent directly to the plant. And I'm going to show you the plant, and then everything sent to the plant. The plant will convert it into 6 individual motor speeds, and then it's going to send that out to the ESCs. Now we're going to show you the plant. This is all the code. This is actually the wrong page. This is system.cpp. So bear with me. This is the update system function. This call right here is going to call update on all sensors. Basically, it's updating all the sensory information. It's going to come down. Delta time is the integration constant. It's basically grabbing from the virtual timer, basically the integration constant. This block of code, basically if it detects input from the RC receiver to release the cargo, it'll set 2 ports. It has a 3-second timer that if the motors, the linear actuators in the cargo subsystem are active, it will kill those motors after 3 seconds. That way those motors are not continuously draining current while it's running. AHRS, that stands for Attitude Heading and Reference System. That is basically the data fusion update. It's pulling data from the gyroscope, magnetometer, and accelerometer, and then it's outputting out to the orientation. It's also going to provide the feedback loop for the yaw control as well. Then here's our fun part. This is a correction, an offset correction for the roll. The roll is about 180 degrees off. The flight computer is correcting that. We got current ones. This is our PID controller outputs. We have 3 of them here. There's the PID control for the roll, then you have it for the pitch, and then there is it for the yaw. After this, it's going to basically determine the initial thrust. So pitch thrust, it's going to declare that variable. It's going to take the inertia calculated that Matt has calculated for the pitch. It's going to take our desired acceleration. It's going to convert that into degrees, and then it's going to multiply that by our incoming pitch signal. Basically, the input from the radio receiver is essentially a scale value for the acceleration. And then, of course, there's the length of the arm there. Same for thrust. We're taking the inertia, multiplying it by the desired acceleration, converting that to degrees. The acceleration is scaled based on the input coming in from the roll, and then you divide it by the length of the arm. And basically what this is doing is this is calculating the necessary force or thrust that specific motor needs to output in order to complete that maneuver. Same with yaw. Yaw is a little bit different. We basically multiplied the inertia by the acceleration by the scaling value, and then that is divided by yaw R1 minus R2. Those two radiuses, this is the radius from the center of the drone to the inside part of the propeller blade. This is to the outside of the propeller blade. So we're taking that difference. That gives us the thrust to the yaw. And then we're also calculating a total thrust. Total thrust is the thrust of all 6 motors put together. And then now right here is the delta roll and the delta pitch values that it's calculating. Basically what delta roll and delta pitch is, as the drone rolls or pitches, there's a loss of thrust due to a cosine. Basically the thrust vector is pointed at an angle, and in order for the drone to maintain its altitude, we need to take the cosine of that angle and determine that the actual vector that's pointing down towards the earth. And basically it's calculating delta roll and delta pitch is the additional thrust that the motors need to output in order to keep the drone to maintain its altitude during the roll or pitch maneuver. Down here it's then calculating the thrust for each of the 6 motors based on this. This is basically establishing a baseline. It takes the weight of the motor divided by 6, and then we calculate our baseline thrust based on the throttle. If we're pitching forward, it's going to adjust motors 2 and 4, which are the back motors. If we're pitching back, it's going to adjust motors 1 and 3 based on how much thrust we need to go. Roll, same thing, except this is motor 6 and 5. And then all 6 motors are being used for yaw. 1, 2, and 6 are spinning in one direction, 3, 4, and 5 are spinning in the other. Basically for a yaw, either 1 or 2 cases is going to happen. Either 1, 2, and 6 are going to throttle up, and 3, 4, and 5 are going to throttle down, or vice versa. Then we have our delta roll and delta pitch corrections, basically adding that additional thrust needed to maintain altitude during the maneuver. Then what we're going to do is we're going to take that thrust, we're going to convert it into throttle. You have the input throttle as a baseline, and then you have the thrusting value being calculated. This equation right here is coming from Matt's calculations done in the fall. And then after that is going to issue commands to the ESCs to set their throttle to the calculated value. This down here is taking the throttle value and converting it into motor speeds for output to the PC. And this is the actual, let me get the controller. This is the actual output of that plant and control algorithm, as you can see. as you can see, we got increase due to that's basically changing throttle. This is yaw right. This is yaw left. Okay, this is pitch forward. This is pitch back. This is roll left, and this is roll right. And it looks like